All right, hi everyone. My name is Raphael Cervantes. I am a postdoc at Fermilab, and I'm here to talk about using ultra-high Q SRF cavities to search for Wavelike Dark Matter, more specifically dark photons and axions. Okay, so first I want to introduce our group. So we are the Superconducting Quantum Materials and Systems Center. We are one of the these United States quantum centers that are that's specifically hosted at Fermilab. We are partnered by, our partners include, we have many partners, some of those are listed on the right. And at Fermilab, we are experts at superconducting cavities with Qs of 10 to the 9, 10 to the 10. And they come from the accelerator world, and we're trying to see if we can transfer that technology to axion and dark matter searches to kind of improve the sensitivity and the scan rate of these searches. Okay, so for most of this talk, I'm going to focus on dark photons, because that's the search that I did. Dark matter, it could be made out of anything. A lot of people like WIMPs, axions, but they could also be made out of dark photons. Dark photons, if they exist, would have this kinetic mixing with the standard model photon. So as you can see on the right, it oscillates between the dark photon and the standard model photon. And this oscillation is parameterized by the kinetic mixing angle, or kinetic mixing strength chi. But we don't know what the dark photon mass is or the kinetic mixing strength. So plotted on the left is the available parameter space, the kinetic mixing strength chi versus the dark photon mass. And here are the different experimental exclusions. And to search for the dark photon, we want to push down on the explored parameter space. The way we can look for dark photons, there's a few ways. One way is to try to create our own dark photons in the lab. One prominent example of this is these light shining through wall experiments. An example of a light shining through wall experiment that we did at Fermilab is this dark SRF experiment. And here are the experimental exclusions for that. But you could also assume that dark photons make up all of dark matter, and you can look for it as dark matter. Okay, so the way we look for dark photon, dark matter is very similar to how other experiments look for axions. It's using this microwave haloscope inside of a straw. And I'm not going to go over this because people are probably well familiar with this. What I do want to point out is that you can look for dark photons and axions in pretty much the same way, except for with dark photons. For axions, you need a magnetic field to induce this conversion from an axion to a standard model photon. With dark photons, you don't need that magnetic field. So they will just convert to a standard model photon. You don't need a magnetic field. It actually makes things a lot easier. But these experiments are still really hard to perform. We have this very narrow band detector, this microwave cavity. We're looking for, through a wide range of parameter space, because we don't know what the dark matter mass is. So, and we're looking for a signal that's probably less than 10 to the minus 24 watts. So these experiments are really hard. They're really slow to scan over the available parameter space. So at SQMS, we're thinking about how we can use our expertise to, how we can push, increase the scan rate of these experiments. And we think that a promising way is to use superconducting cavities with, ultra high Qs. So if you compare these niobium cavities with Q of 10 to the 10, there's a factor of 100,000 and improvement in the quality factor. And these higher Qs are important because they allow you to build up a larger signal power, dark matter signal power, and in certain circumstances, they also reduce the noise floor of the experiment. And so what we're going to argue right now is that this actually improves the scan rate by a factor of 100,000. And I mean, I would love to do my experiment 100,000 times faster, and I'm sure I would love for this community to find the dark matter 100,000 times faster. So this is a bit of a controversial statement, so I'm going to go more into it. So in a typical haloscope experiment, the scan rate is proportional to the quality factor. because you're able to, higher quality factors means more coherence time, which allows you to build up a larger signal. But there is a nuance once your cavity quality factor is much larger than the, I guess the distribution, your like dark matter energy distribution from the dark matter halo. As you can see, here's a comparison between a dark matter halo and your cavity bandwidths. So it's been common wisdom in the community that at this regime, you don't win by going to higher quality factors because you're sampling a smaller fraction of the dark matter halo. And yes, that is true. And because of that effect, this signal power levels off once you get to, a Q that's comparable to the quality, the Q dark matter. However, because now your signal power is now confined to a smaller bandwidth, which means that the noise power integrated within the signal is much smaller. And in fact, it decreases by a factor of the quality factor. You win a lot by with the SNR, with the signal to noise ratio. And furthermore, once you're in this regime, you don't have to scan cavity bandwidths by cavity bandwidths. You can actually scan in steps of the dark matter bandwidths because a single cavity frequency is sensitive to a range of dark matter rest masses, either like dark photon or axion rest masses. However, with this tuning scheme, you would only be sensitive to the virialized dark matter. You wouldn't be sensitive to cold streams or axion asteroids. But I think for faster tuning, I think that's worth it. So with all of these effects put together, the scan rate is right here. It's proportional to the quality factor. And if you're still skeptical about that, I posted something on the archive at the beginning of the week. You can look at that and you can try to come and find me. All right, so that said, I think ultra high Q cavity haloscopes are well motivated. And with that, we actually did a proof of principle measurement, or proof of principle dark photon search with an IBM cavity that we just happen to have sitting in a dilution refrigerator already. Here's the cavity. It had a cavity temperature of 45 millikelvin, a loaded quality factor of 8 times 10 to the 9. And it was connected directly to a HEMT amplifier with a noise temperature of 4.9 Kelvin. Right, and the frequency that we're looking at here is 1.3 gigahertz. So we measured the power coming out of the cavity to see if we would find a dark photon signal. That's what it looks like. We didn't find a dark photon, unfortunately. We just measured noise over 1,000 seconds of integration time. But even though we didn't find the dark photon, we were able to use the measured noise to put an exclusion on the kinetic mixing angle, or kinetic mixing at 5.4 microeV, using pretty much the standard haloscope analysis. And we come with the kinetic mixing strengths. We place a 90% exclusion of 2 times 10 to the minus 16. This is great. Here's the same limit compared to other microwave haloscope experiments. It's deeper by almost an order of magnitude. Right, so it's deeper than almost an order of magnitude. It's the deepest exclusion to Wavelike dark photon dark matter. And this was just like with the parasitic measurement using a transistor amplifier. This is pretty low-hanging fruit. Like, we have tons of these niobium cavities. We're going to push more into this direction. Right. So it was the deepest limit, but admittedly, it's also the narrowest limit that there was. So we're developing tunable cavities, SRF cavities right now that would probe more parameter space. Here's an example where you have this cavity and your tuning mechanism is just this this niobium rod that just sticks further into your cavity. The working title for it right now is the plunger cavity. And the projected limits for that are shown right here. And then in a future phase, we're thinking of putting in, a transmon qubit to implement non-demolition photon counting to subvert the quantum noise limit. Okay, so that said, we're excited about our dark photon search, but a lot of people here care about axions more. So I want to talk about the implications of ultra-high Q cavities for axion searches. So just as a data experiment, let's take the same experiment, the same data, and pretend there was an 8 Tesla magnetic field. This is the limit that we would have. It's 4 times 10 to the minus 16 this J gamma gamma, which is half of the DFSE limit. It just kind of crashes through the the QCD axion parameter space, and that was just with a single cavity and a Hams amplifier. So a direction for searching the QCD axion seems pretty simple. We just got to make 10 out of 10 cavities work in multi-Tesla magnetic fields. But cavities don't, superconductors don't like magnetic fields. But we are, believe it or not, are making a lot of progress towards this front. Here is the progress we're making at Fermilab. We're developing this niobium 310 cavity to look. And we've measured a quality factor of about 5 times 10 to the 5 already, with some room for improvement. And then, of course, there are other people in the community that are making great progress on this front, some of which was presented at this very meeting. All right, so practical, I want to leave off with practical considerations for developing SRF haloscopes, because things that other haloscope experiments have yet to worry about. One is you have to worry about, once you get to high enough Q, you have to worry about cavity vibrations, and it creates this modulating signal of the dark matter signal, which can be dealt with, but it's annoying. The other thing is you have to worry about the ring up time and ring down time of these cavities, especially if once their coherence times is over 10 seconds, which makes it just annoying to operate. And then I'll reiterate, the tuning strategy does not capture non-virialized dark matter. So I also just want to make a shout out to other axion searches that we're doing at SQMS with these multi-mode cavities. You should talk to Bianca Giacone about those. They're really interesting, and I want to thank the money that comes from the Department of Energy, and this is our wonderful team at Fermilab, and I will now take any questions.
Thank you very much, Raphael. Yeah, please come forward with your questions. Yeah, we have one in the back.
Yeah, thank you very much for the nice talk. You showed also some first results on superconducting cavities in magnetic fields.
Yes.
And I just compared to what CUP was doing. So in the CUP results, if I remember correctly, you see first an increase of the Q in magnetic fields, and then a decrease, while you show a decrease right from start. Can you just briefly explain this to me?
That is a question for Sam Posen, who did this measurement. He has an explanation. I've forgotten about it. I don't know personally.
Okay. Good. Thanks.
Jonas seems to have an answer for this.
I can respond to Axel's question. It's the substrate. What Dano showed is a substrate in our case. Mm-hmm. So we are dealing with that. It's a different physics. Yeah, this is sputtered, right? You put it directly on the metal. So it's entirely different physics.
Thanks for the great talk. So you mentioned microphonics and vibrations.
Yes.
I'd imagine with such narrow line widths, they have to be very carefully shielded from vibrations. Can you give us an idea of yeah, there you go. Thank you.
Idea of what exactly? Keep going with your question.
Well, my question is, can you give us an idea of whether or not you characterize this and how good this isolation has to be?
Oh, yeah. So we can measure the oscillations directly several ways. Here is just using a self-excitation loop, and you can see all the sidebands. Yeah, you can directly measure the power that goes into the sidebands. We're good? All right. Okay.
Any more? Yeah. Last one in the back.
So hi, thanks for the great talk. So I was wondering, when you talk about the scan rate, and you mentioned that when you have a narrower quality factor, you have less noise. And that's fine as long as you use an amplifier. But you mentioned also that at some point you would like to use a photon counter. So how does the scan rate change in that case?
That I have not worked out yet. My naive intuition in my head is that you can just you can just remove the noise from the noise temperature from the amplifier and replace it with some sort of dark count rate. But that's something I need to work through.
Was there a follow-up question, or no? You asked the last one, right? Okay, great. Any more quick question? Like we have time for one more, maybe. Yes.
Could you please explain a bit more about the TLS dissipation problem?
Oh, yeah. So there is a, TLS stands for two-level systems. Usually when you build these WIMP cavities, you end up with some sort of oxide layer. And once you get to low enough temperatures, like less than 1 Kelvin, these two-level system effects starts to take effect, and you just get more dissipation from this oxide layer. And it kind of kills, if you look at the quality factor versus the temperature, for this system, it maximizes at 1 Kelvin. Like, say you have like a Q of 10 to the 11, and then once you get to like dilution refrigerator temperatures, your Q goes down by an order of magnitude, which is very sad.
All right, then let's thank Raphael again.